numerical methods, the sign change method. Example 1. So we want to solve this equation, but not using an algebraic method, but using the sign change method as the first step. So we take all the terms to one side, so we have f of x equals 0, and this is our function of x here, equals 0. This graph is of y is equal to f of x, this. And we can see that there are 1, 2, 3 distinct roots, and one of the roots is in this interval between x equals 2 and x equals 3, this root here. So using x equals 2 in here, the y coordinate at that point is negative, it's -1 right there. Using x equals 3 in here, now the y coordinate is 1, so when x equals 3 the y coordinate here is 1, it's positive. We have a sign change. Now if there was no sketch available and we tried these numbers and we got a sign change, I would say there is at least one root between x equals 2 and x equals 3, and because there's a sign change there, the number of roots would be odd, but we can clearly see from our sketch here that between x equals 2 and x equals 3 there is a single root right here in that interval. So it would be more correct or more appropriate for us to say that there is a sign change, hence one root between x equals 2 and x equals 3. Example 2. We have an equation that we're going to attempt to solve numerically, not algebraically, and we're just doing the first step, the sign change method, just like in the first example, to show that there's a root present in a given interval. We're not actually working out the roots. We need to use the iteration method and the Newton-Raphson method to do that part. So we need all the terms on one side, like so, and it doesn't matter which side you move them onto, as long as they're all on one side and you've got 0 on the other side. So this is my function of x. It's in this form now. Okay, so now we need to substitute both of these values of x into here. The calculator needs to be in radians mode. So 5/4 pi here, and 3/2 pi in this one, and the calculator gives this value, which is negative, and this value, which is positive. So we have a sign change. So at this stage we can say there is at least one root in the interval, but the question does say show that there is a root, not roots. So we know there is one root in this interval, and we can investigate further by looking at some graphs. So I'm going to start by sketching the graph of cos x, and I'm going to sketch the graph of 4 minus x. So both of them together on the same graph. Okay, so this is the first method. There's actually two methods we can use here. So cos x and 4 minus x, both of them together. So we get this graph. And what the graph shows is that in this interval, and the interval is here, that's the same as this, both graphs intersect, which means these equations are equal to each other right here for this value of x. This value of x is the solution to this equation. It's the value of x where the graphs are intersecting. It's our root. And we can see that in the interval there is only one point of intersection, one root. An alternative method is to start with this equation again, take all the terms to one side. So this is our function of x. So we want to sketch y equals f of x, which is this. So again, this is the graph we've got this time, and this interval is here, and we're looking for where the graph crosses the x-axis. So that's where y is equal to 0, and that is this point here. So the x-coordinate here is exactly the same as the x-coordinate here. We're using a different approach, different graphs, but that point there, the x-coordinate is exactly the same as this. And again, we can see that in the interval there is only one root. So that's all we've shown with this method, with the sign change method, is that there is the presence of a root in a given interval. Then we can investigate further to work out the actual value of that root. And again, that's using the iteration methods and Newton-Raphson and so on. Okay, example 3, part A, we're using graphs to show that there's only one positive root for this equation. So graphically we need to show that the two graphs only intersect at one point. So we're going to sketch y equals ln x and y equals 1 over x on the same graph and look for points of intersection. Okay, so here are the graphs. So it's color coded, that's the red one, that's the blue one there, and we can see there's only one point of intersection, that point there. So one root, and the graphs intersect at x equals alpha, this point. The x coordinate there I've referred to as alpha. So this is a solution to this equation. So if ln x equals 1 over x and x equals alpha, then ln alpha equals 1 over alpha. Okay, part B, we have to show that there's a root, a single root, in the given interval. So these are not coordinates. We're using interval notation, so x greater than 1.7, x less than 1.8, so in that interval. So we have the equation. Take everything to one side, so the whole thing is equal to 0. So it's in this form: f of x equals 0. Function of x here on the left hand side equals 0. Okay, so we substitute in x equals 1.7 into our function like this, and that's the value we get, it's negative. Then we substitute in x equals 1.8 into our function, and we get a positive value. There's a sign change, and a sign change is showing that there is a root. We know there's one root, we've seen that on the graph, so there is definitely a root in the interval x equals 1.7 to x equals 1.8. So we haven't worked out the actual solution to this equation. All we've shown is it's in quite a narrow interval. It's in this interval. Okay, part C, we have to show that alpha, the solution to our equation, is 1.763 to 3 decimal places. So when we're rounding to 3 decimal places, we need to consider what would be here for the 4th decimal place. Okay, so we're going to look at these two digits. So anything from 1.7625 all the way up to, but not including, 1.7635 will round to 1.763 to 3 decimal places. So we need to look at these digits here, and I've got these on a number line here. So anything in this interval here, any value in that interval will round to 1.763. Okay, so now I'm going to use these values for my new interval. So I substitute them into our function of x, and again we're looking for a sign change. That's negative, that's positive, we have a sign change, so we can say that we've narrowed alpha down to this interval, which rounds to 1.763. For practice, try these questions.